Welcome to this series of videos on the evolution of neural networks. In it, we'll look at some of the major innovations and groundbreaking milestones in this exciting and evolving area. If you're unfamiliar with neural networks or AI, then stay tuned. Some links at the end of the video will get you up to speed on this topic. In the late 1980s and early 1990s, researchers in the field of artificial intelligence were faced with a daunting challenge: how to process sequential data such as time series, speech signals, and natural language processing. Feedforward neural networks had proven to be good classifiers. This type of AI was shown to be very effective and adaptable for problems such as credit scoring, with fixed inputs and fixed outputs. This was true both in the retail space for problems such as credit card or loan approval, as well as in capital markets for onboarding hedge funds to a bank's prime brokerage platform. However, simple feed-forward networks suffered from inflexibility. Having fixed numbers of input neurons as well as fixed numbers of outputs made them unsuitable for time series, speech, or text, which are all characterized by variable length sequences. Researchers and practitioners needed a model that could capture the complex temporal dependencies in such data. This led to the development of a family of recurrent neural networks, or RNNs, the solution that emerged to solve this challenge and become one of the most powerful tools in the field of machine learning. One of the first of these was the Elman Network. In 1990, Jeffrey Elman introduced a simple feedback loop architecture that maintained a hidden state to process sequential data. This network, now known as the Elman Network, was the first RNN architecture. It introduced a context layer that maintained a hidden state, updated every time step. This hidden state serves as a memory of the network's previous inputs and allows it to capture long-term dependencies in the sequence. In the diagram on the screen, you can see a simple network with two input neurons, two output neurons, a single hidden layer of 3 neurons, along with a context layer, also of 3 neurons. The weights and the activations of the context layer memory mean that the network is not simply reacting to the current inputs. In addition, it's holding information from all of the inputs that the network has seen previously. We can add additional neurons to the input layer to increase the length of the input sequence. These types of networks have been used to automate market-making spreads, automatically updating the bid and offer prices that market makers submit to exchanges in response to price sequences. They can also be used to respond to prices to determine if a portfolio manager should be underweight or overweight a particular asset. And they've also been used in predictive text language models to predict the next word or token in a sequence. While the Elman network is being trained, the context layer's weights are updated along with the other weights in the network using backpropagation. The goal of training is to learn the optimal values of the weights in the network, including the context layer's weights that minimize the error between the network's predicted output and the actual output. It's learning how to adapt its memory. As well as time series applications in finance, Elman networks have been successfully deployed in weather forecasting systems, taking in time series of atmospheric pressure, temperature, and wind speed. While Elman networks are a powerful tool for processing sequential data, they're not without their challenges. Here are two in particular. Elman networks can suffer from the vanishing and exploding gradient problem. This occurs because the network's hidden state is updated at each time step based on the current input and the previous hidden state. During backpropagation, the gradients are propagated through time from the output back to the first time step. This means that the gradients have to be multiplied by the same weight matrix at each time step. You know that if you multiply the same number by itself enough times, you'll get a problem. If the number is less than 1, you will eventually get 0. And if the number is greater than 1, you will eventually get infinity. The same thing is true for matrices if the eigenvalues are either greater or less than 1. There are also difficulties capturing long-term dependencies. While the context layer in Elman networks helps the network capture medium-ish term dependencies in the sequence, the values will eventually fade. It can therefore be difficult for the network to maintain a memory of its previous states over very long sequences. These two problems, those of the vanishing and exploding gradients and the long-term memory issue, motivated a more modern architecture, the LSTM, or Long Short-Term Memory Network. We'll discuss this architecture in depth in the next video. This is Richard Walker from Lucidate. Thanks for watching this video on the evolution of neural networks. In this episode, we looked at the Elman Network, one of the first recurrent neural networks that was developed to solve the challenge of processing sequential data. We saw how the Elman network uses a feedback loop architecture and a context layer to maintain a hidden state or memory for capturing medium-term dependencies in the sequence. We discussed some of the real-world applications of Elman networks, including finance, weather forecasting, and predictive text language models. As we saw, Elman networks are not without their challenges, such as the vanishing and exploding gradients problem and difficulty in capturing very long-term dependencies. These challenges motivated the development of more modern architectures, such as the Long Short-Term Memory Network, which we'll discuss in the next video. As promised, here are some links to get you up to speed with AI and neural networks, or act as a refresher if your knowledge is a little rusty. The first link is to a playlist of 5 60-second videos to give you the context of what neural networks are all about. The second is a link to a playlist that goes into more detail. It covers different neural network architectures, different activation functions, and the backpropagation algorithm. If you like these videos or have a request for different content, then drop me a comment. If you enjoyed this video, please give it a thumbs up and leave a comment below. Don't forget to subscribe to Lucidate's channel for more videos on the exciting and evolving field of artificial intelligence. Thank you for watching, and we'll see you in the next video.